Hi students, welcome to this course, PLC Automation, an Introduction to Programmable Logic Controller. I am Professor Yao. PID Principles. The keywords: control tasks at a set level, the desired set point, promptly and accurately, cubic feet per minute, CFM, ratio control, the deviation of a process, air vent damper, an offset error, rate control, the process variable, a control panel, a variable speed drive, a dial setting, a flow sensor, feedback. PID, or proportional, integral, and derivative, is an effective control system for continuous process that performs two control tasks. First, PID control keeps the output at a set level, even though varying process parameters may tend to cause the output to vary from the desired set point. Second, PID promptly and accurately changes the process level from one set point level to another set point level. For background, we briefly discussed the characteristics of each of the PID control components: proportional, integral, and derivatives. Proportional control, also known as ratio control, is a control system that corrects the deviation of a process from the set level back toward the set point. The correction is proportional to the amount of error. For example, suppose we have a set point of 575 cubic feet per minute, CFM, in an airflow system. If the flow rises to 480 CFM, a corrective signal is applied to the controlling air vent damper to reduce the flow back to 575 CFM. If the flow somehow rises to 585 CFM, twice the deviation from the set point, a corrective signal of 4 times of the magnitude would be applied for correction. The larger corrective signal theoretically gives a faster return to 575 CFM. In actuality, the fast correction is not precise. You return to a new set point at the end of the correction. For example, 476.5 CFM, not 575 CFM. Proportional control does not usually work effectively by itself, resulting in an offset error. To return the flow to the original set point, integral control, also known as reset control, is added. Note that integral control cannot be used by itself. Remember, with proportional control only, we had an output error from our original set point. We ended up to 576.5 CFM, not 575 CFM. Integral control sends the product of the error, 1.5 CFM, and the time the error has persisted. A signal is developed from this product. Integral control then uses this product signal to return to the original set point. In a controller, the added integral signal reduces the error signal that caused the output deviation from the set point. Therefore, over a period of time, the process deviation from our original 575 CFM is reduced to minimum. However, this correction takes a relatively long period of time. To speed up the return to process control, point deviation control is added to the proportional integral system. Derivative control, also known as rate control. Produce a corrective signal based on the rate of change of the signal. The faster the change from the set point, the larger the corrective signal. The derivative signal is added to the proportional integral system. This gives us faster action than the proportional integral system signal alone. A typical PID control system is shown in block diagram form in figure 23.1. This configuration is the commonly used parallel type. The controller output signal of figure 23.1 is utilized through a control system to return the process variable to the set point. This figure shows the block diagram of a typical PID controller. An illustration of a system using PID control is shown in figure 23.2. In this system, we need a precise oil output flow rate. The flow rate is controlled by pump motor speed. The pump motor speed is controlled through a control panel consisting of a variable speed drive. This picture shows the general control system diagram of hydraulic pump. In turn, the drive speed control output is controlled by an electronic controller. The electronic controller output to the drive is determined by two factors. The first factor is the set point determined by a dial setting or equivalent devices. Second, a flow sensor feeds back the actual outpoint flow rate to the electronic controller. The electronic controller compares the set point and actual flow. If they differ for some reason, a corrective signal change is sent to the motor controller. The motor controller changes motor speed accordingly by changing the voltage applied to the motor. For example, if the output oil flow rate goes below the set point, a signal to speed up the motor is sent. The controller then uses PID control to make the correction promptly and accurately to return to the set point flow. If the dial is changed to a new setting, the function of the PID system is to reach the flow at the new set point as quickly and accurately as possible. Homework: handwriting all keywords and submitting them to Coach Facebook. Just do the online quiz and see you next time.